information. Statistics is like a story that goes on and on and on. I need you to pay attention now to what I want to explain now. Okay, the Rao-Blackwell theorem and minimum variance unbiased estimation. Now, I need you to take a look at this. The Rao and Blackwell, okay, actually came together. When I say Rao, I'm referring to C.R. Rao, the popular C.R. Rao in statistics, and David Blackwell. They came together and they give us a theorem, and that very theorem can actually be used to figure out, we can use it to improve on the efficiency of our estimator. How can we do that? They actually use the knowledge of sufficient statistics. Okay. Now, using the knowledge, which means before I can use a Rao-Blackwell theorem, I need to first obtain my sufficient statistic. I can obtain my sufficient statistic whether through Lemma factorization or Lemma-Skefield theorem. But the most popular one is Lemma factorization. Okay. Now, what am I going to do? Okay. That was why I said sufficient statistics play an important role in finding good estimators. I told you there's a difference between statistic and estimator. Okay. Now, if a theta cap is an unbiased estimator for theta, let's say we know theta cap, an unbiased estimator for theta, it could be sample mean, unbiased estimator for population mean. Then if U is a statistic, what is the statistic for mean summation Y? Does that make sense? Okay, if U is a statistic that is sufficient for theta, how do we know it's going to be sufficient for theta? Maybe we have used a Lemma factorization theorem or Lemma-Skefield theorem or the conventional conditional distribution theorem, approach to arrive at a sufficient statistic. Okay, then there is a function of U. Okay, a function of U is like a function of a sufficient statistic. A function of U that is also an unbiased estimator for theta and no larger variance than theta cap. What are we trying to say? I'm gonna give you this. There was a paper in 1945 by C.R. Rao and another article in 1947 by David Blackwell. Okay, C. Rao in 1945, released an article called Information and Accuracy, okay, in the estimation of statistical parameters. In the estimation, you can check on this paper. Okay, this was actually published in 1945 by C.R. Rao in the Calcutta Bulletin of Mathematical Society. And of course, in 1947, Blackwell, David, 1947, talk about conditional expectation and unbiased sequential estimation, and this was published in the Annals of Mathematical Statistics. Okay, so Rao and Blackwell came together and they gave us a theorem called Rao-Blackwell theorem. The Rao-Blackwell theorem is actually a theorem used to improve on the on our estimator, on the efficiency of our estimator. And how do they do it? The way they do it is this. I'm going to demonstrate that to you now. This is the way they do it. Take a look at this guy. initially we have a theta cap that is an unbiased estimator that we have already identified, and maybe by Fisher-Neyman factorization or by Neyman-Skeffey theorem, we obtain a U, which is a sufficient statistic. Now, when we do the conditional expectation, take a look at that. Expected value of a theta cap given U means expectation of an estimator giving sufficient statistic. Okay, we believe that that is actually going to be another estimator. That was why you see theta cap star. Okay, so what was the intention of Rao and Blackwell? Their intention is to improve on the efficiency of a theta cap. Does that make sense? So if I want to improve on the efficiency of a theta cap, you take a look at theta cap. Theta cap is unbiased, and this guy also unbiased. How many unbiased estimator do I have? I got 2 unbiased estimator. Okay, and the reason why the Rao Blackwellization is actually good is because the variance associated with the improved estimator is less than the variance of the estimator we started with. And how am I going to know? If you take a look at this is to show that the new estimator is unbiased, then the variance of the new estimator, like I call theta cap star, will be less or equal to that. So which means there have been an improvement, okay, on the estimator we started with. Okay, now the new estimator, okay, the theta cap star is what we're going to call Rao Blackwell estimator. Okay, the process of transforming an estimator, okay, the process of transforming an estimator, putting into consideration the conditional distribution, conditional expectation of the conventional estimator and the sufficient statistic is actually what we call Rao Blackwellization. That is the process. The resulting estimation is a Rao Blackwell estimator. Okay, now I think you can see that that's what we call Rao Blackwell theorem. The bottom line, the Rao Blackwell theorem enable us to be able to improve on the efficiency of our estimator using the idea of a sufficient statistic, and by considering the conditional distribution or the conditional expectation of the estimator giving sufficient statistic. Okay, take a look at this. Now the question now is, how do I actually know that, they measure something here? If you take a look at this is like telling us the variance of the new estimator will be less than the variance of the conventional estimator. How are we going? I'm actually going to show you that, but that was what they mentioned here. That was what they mentioned here. It said, then there is a function of U that is also an unbiased estimator for theta and has no larger variance. It has no larger variance than the conventional estimator. How are we going to show that? Please, I need you to actually be focused right now. I want to show that. I first want to show you how the improved estimator is unbiased. I also want to show you how the improved estimator has a smaller variance, because that would justify the Rao Blackwell efforts. Okay, take a look at this. This is how we're going to show for that the new estimator is unbiased. The new estimator is a conditional expectation of the old estimator giving the sufficient statistic. So the theta cap star is expected value. Let me do this so that you understand what I mean. This guy, everything inside that parenthesis is the same thing as that guy. Okay, Now, when I now want to find the expectation of that is to investigate whether it's unbiased or not. And that's why you have another expectation here. But the fact that if you take a look at this guy is an estimator, okay? And you know, the theta cap giving you, take a look at this. Theta cap giving you, that should be theta cap. Okay, just like I'm saying, you know, theta cap is y bar, u is summation y, right? If I know summation y, then I already know y bar. Does that make sense? And that is the reason why we're actually going to say on average. Expectation inside is going to say on average, theta cap giving you is theta cap. Does that make sense? On average, theta cap giving you is theta cap. Now that was how I got that one. Of course, expected value of theta cap equal to that. Now, how am I going to show for the variance? I needed to pay attention now on how to show the variance whenever we're dealing, you know, our random variable here is conditional expectation. Please, I need you to pay attention. If you don't understand, you ask me question. Now, let me tell you this. Our random variable here, theta cap star, is this. This is our random variable. Okay, if this guy is our random variable, okay, we now want to find the variance of this guy. But because this is a conditional expectation, it's actually going to come in two ways. It's going to be variance of that conditional expectation plus expectation of the variance. That's according to statistical theory. Whenever I actually have a conditional expectation to be a random variable and I want to figure out the variance, you can check what you've done in star 4101 in the textbook. You're actually going to see something like this. Okay? Now, what is this guy inside the parentheses is theta star, right? And you know, that's going to be variance of theta cap equal to this plus this guy. Okay? And let me tell you this. This is not going to be equal to this because this guy is positive. Of course, the variance, you know, this is not variance. We don't expect variance to give us negative. By the time we take that, so, and that was the reason why I said because the variance, you know, what I have inside here, you know, it's actually going to be greater or equal to 0. Let me just say it could be 0 or greater than 0. Okay, then we're going to have that. And that was the reason why we said the variance of theta cap. This is the variance of the estimator we started with. This is the variance of the improved estimator. Okay, this is going to be greater or equal to this, means this is going to be less or equal to that. And that is going to be called minimum unbiased estimator. It means in a class of unbiased estimator, that guy is going to have the minimum variance. I want us to go into an example now. Okay, what are we looking for? This time around, we're no longer looking for sufficiency, but we're looking for minimum variance unbiased estimator. And one of the ways to figure out minimum variance unbiased estimator is actually to go by sufficiency. You know, for us, identify sufficiency, and after identify sufficiency, consider the conditional distribution of the estimator giving sufficient statistic. But let me tell you this. What I want to do now is not the only way to you know, to figure out minimum variance unbiased estimator. That is the reason why on Monday, I'm actually going to walk you through another way to figure out minimum variance unbiased estimator. Another way to figure out minimum variance unbiased estimator that we are actually going to do on Monday is what we call Kramer-Rao lower bound. Kramer and Rao lower bound. Okay, the same Rao and Kramer, they work together and they gave us a lower bound for the variance. Okay, so that's another way to obtain minimum variance unbiased estimator. We're going to do that on Monday. And another way to obtain minimum variance unbiased estimator is to investigate exponential family of distribution. Exponential family of distribution. So these are like other ways. Okay, other ways to obtain minimal variance unbiased estimator, but these are reserved for Monday. But the one I want to walk you through now, okay, the one I want to walk you through now is using the idea of Rao-Blackwell theorem. Okay, now, any question before moving forward? Okay, I should go back, right? You know, whenever a random variable is conditional, you're always going to use this. Do you know what I mean by conditional? This is theta cap giving you. That's a conditional. This is not theta cap over you. This is theta cap giving you. You remember when we were investigating sufficiency the other time? I said a conditional distribution giving. So it's the same thing here. This is a conditional function. No, this is an estimator. Estimator giving sufficient statistic. No, 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 no. This is conditional. This one? No, no, no. This what we're trying to say here is we want to find the variance of unconditional, okay, the variance of the estimator. What we're not trying to say, it's just like you are talking about in Bayes theorem. You talk about total probability. You know, in the Bayes theorem, like I want to find the probability of yes, or maybe somebody tests for COVID and the machine say positive. Now, what is the total probability? Now, machine can say positive and the disease is present, or machine can say positive, disease is not present. That will require the plus. So these are like possibility of the variances, which means the unconditional estimator is total. Does that make sense? So which is adding the conditional to conditional. You understand? So what I'm trying to say is this. I want to get variance of y and y condition on s. Okay, so this is going to be variance expectation, okay, of y given x plus expectation variance of y given s. This exists in statistical theory. So if I were you, you know what you're going to do? Check 4101 textbook. So whenever we want to find if y, okay, if y has a tendency to depend on x and I want to find the variance of y, you know, I'm only going to find variance of y if there's no connection between y and s. But here we are deliberately, because the Rao-Blackwell theorem enabled us, you know, they were able to improve on the efficiency of estimator, you know, trying to consider the conditional distribution of the conventional estimator given the statistic. Does that make sense? Okay, so that is why we have that. Now take a look at this. Let y1 or y2 up to yn come, you know, from a Bernoulli random variable. There's a lot in this question. Okay, I needed to take a look at that. There's a lot in this question. They've given you the distribution, and they ask you use factorization theorem to find sufficient statistic. Okay, then that summarizes the data. Then give MVUE for P. MVU, minimum variance unbiased estimator. Okay, now you want to first get sufficient statistic. This is how to get sufficient statistic. You know, I've walked you through this, right? This is by Nemer-Fisher factorization approach. Now, after getting this, what is the sufficient statistic here? It is summation y. Is summation y an estimator? No. What is an estimator here? P cap. What is P cap? Summation y over n. What does that mean? Summation y, look at that. Summation y over n. This is the estimator. What is it telling you? Estimator is a function of sufficient statistic. Do you see that? Because in the estimator, there is summation y, which is a sufficient statistic. And that was why, if you take a look at my conclusion here, according to the factorization theorem, U is summation y. You know, here I'm using U to denote sufficient statistic. And of course, it's a summation y. Okay, because summation y is part of where you have the information after factorizing. Does that make sense? And right now, U equal to summation y, which we believe is sufficient for P. Now, the statistic best summarizes the information about parameter P. Now, let us now take a look at this. What is U? Oh, U is summation y. And if U is summation y and each y is Bernoulli, the sum of y will be binomial. Does that make sense? If sum of y is binomial, I need you to take a look at this now. If sum of y is binomial, then expected value of U will be what? Will be NP. Okay, expected value of U is equal to NP. Now, what is another way to write that? If I now want to write, now I need to look at this now. I now want to write that U now to be to have a function of something else. What is U? Okay, if I have expected value of U equal to NP, I can also write expected value of U divided by N equal to P. And which means, what is U divided by N? U is summation y. Summation y divided by N is y bar. Okay, what am I trying to say here? I'm trying to say there's a difference between statistic and estimator. Statistic here is summation y, but the estimator is summation y over n, because U is summation y. Okay, then because of that, I'm going to say because this estimator, which estimator? This guy, it's an estimator, y bar is an estimator, and that estimator contains what? Can somebody tell me? The estimator here contains what? The estimator contains sufficient statistic. What is the sufficient statistic? U. Your estimator contains that. If your estimator contains sufficient statistic, then it's actually going to be a very good estimator. Okay, and that was why, because the estimator is a function of a sufficient statistic. Don't forget summation y is U here. Okay, the estimator P cap equal to y bar, then it's going to be the minimum variance unbiased estimator for P, period. Any question? That is how that is done. Any question? Okay, now I'm going to go into another one. This is another question. Let me see. Yeah, I think I've already done that. Now, let's go to another distribution. We've talked about Bernoulli, right? And let me tell you this. We got a situation where you actually need to use the idea of 4101. Okay? Now, because of time, it may not be easy the way we've done that under Bernoulli right now. Now, let's take a look at the next distribution. Suppose y1 up to yn, we got this distribution, Weibull density. Now, find a minimum variance unbiased estimator for theta. What am I going to do? Okay, I can decide to go, if I want to go by way of Blackwell theorem, then I need to get my sufficient statistic using Fisher-Nehmer factorization. Okay, we've done this. Any question? This is super easy. We've done this before, where when you have a distribution, you get the likelihood of the distribution, then you factorize the distribution into 2 in such a way that one is going to contain parameter and the other one is not going to contain parameter. Now we have succeeded in doing that here. Take a look at that. This doesn't contain parameter. This contains parameter. We splitted the likelihood function of this distribution into two. Now, part of this that contain parameter, the summation y squared is a sufficient statistic. But can we say it's an estimator? Is it an estimator? No. But it's just a sufficient statistic. Does that make sense? Now, the moment you obtain your sufficient statistic, we can apply our Blackwell theorem obtaining a minimum variance unbiased estimator. Don't forget our Blackwell theorem. Okay, that's what they do. Now, take a look at this now. I've already discovered that my sufficient statistic is summation y squared using NEMA factorization. But what do I want to do now? We want to find a function of that. Don't forget, okay? Estimator is a function of a sufficient statistic. I'm going to say that again. An estimator is a function of a sufficient statistic. Now, we now want to find a function of this statistic that is also what? Unbiased. Don't forget the other time I said expected value of a theta star car. Okay? Now, I'm now going to take, if from this particular sufficient statistic, I can concentrate on just y squared, and I'm going to call it a new variable, w equal to y squared. Okay? Initially, what do I have? Summation y squared, right? I can just pick on y squared. And if I pick on y squared, where I have a new variable, w equal to y squared, you need to go back to chapter 6. Yeah, chapter 6, star 4101. That talk about the function, the distribution function of a random variable. Now I'm working w equal to y squared. And the initial, what is the distribution of y? The distribution of y is UMVUE. I want to go from the distribution of y to distribution of y squared, where y squared is w, okay? Then I'm actually going to use the idea of a Jacobian transformation. That's what I'm doing here. Take a look at this guy. This is the formula. I want to go from f of y to f of y squared, and y squared is w. What I'm going to do, I'm actually going to plug in what is y. Y is going to be square root of w. Wherever I see y in the density, in the conventional density, I'm actually going to put square root of w, then multiply by Jacobian. The Jacobian is, I'm actually going to do the y, the w. Does that make sense? And y is the square root of w, and that's going to give us this. That's going to lead to this. That's going to lead to this. And I have a new distribution now. What is that distribution called? That's exponential. It means if y follow UMVUE density, y square follow exponential. Don't forget, y square is w now. Okay? Now, if you take a look at that distribution for exponential distribution, what is the expected value of w? That would be theta, right? What is the variance? Theta squared. Okay? Now, what is the expected value of w is theta? That was why you can see me here, right? You can see this guy. Because expected, looking at that distribution, expected value of y is theta, and expected value of w is theta, and w is y squared. Expected value of y squared equal to that. This is going to be theta. Now, if that happened, don't forget the w, I said y squared. But what was the sufficient statistic? Summation y squared. Then I'm bringing that guy back, summation back. Okay, now if I bring a summation, if this guy is theta, when I bring summation, because summation sum from 1 to n is going to be n theta. Look at that. That's not interesting. It's going to be n theta. Okay, now if that is n theta, if I remove the expectation, and theta cap is going to be this guy. Oh my God. This is an estimator. An estimator contains sufficient statistic. Can you see that? And that was why I said It's an unbiased estimator of theta that's a function of sufficient statistics summation y squared. Therefore, theta cap is uniform minimum variance unbiased estimator. You can see at the end of the day, your estimator is a function of a sufficient statistic. A situation where your estimator is a function of sufficient statistic, that estimator will have a minimum variance. It will be unbiased, and it's also going to have a minimum variance. That's what I'm driving at. Okay? I think I put a lot of examples. These are not for normal distribution. Find the minimum variance. You can say I put X because I get two parameters. And the other time, you remember, we actually derived a joint sufficient statistic for normal, which was summation y and summation y squared. Do you remember? Is this. We did it before. We're going to have two, because we got two numbers of parameters. The sufficient statistic for mean is this, for variance is this. But are these estimator? No, they are not estimator. What is the estimator for variance? This guy, sample variance. And sample variance contain sufficient statistic. Look at that. What is going to be the estimator for mean? Y bar. Y bar will contain summation y. And that was why I said, and you know, we have proved in this class, Y bar, the sample mean, is an unbiased estimator for population mean. Sample variance, an unbiased estimator for population variance. Because of that, I'm actually going to say that, you know, we have established the minimum variance unbiased estimator for mu and sigma square. What I'm trying to say, S squared, the sample variance, and the sample mean, they are minimum they are minimum variance unbiased estimator for both mu and sigma squared. You know, if you're able to establish the fact that if your estimator is a function of a sufficient statistic, then that estimator, by Blackwell theorem, qualify to be a minimum variance unbiased estimator. I think I put a lot of examples. You can try this. Okay. Then let me see my time. You can read up this guy as well. Okay, I think I put a lot of examples that I'm actually going to ask my TA to walk you through in class. But you know what? To obtain a minimum variance unbiased estimator, it is not only through our Blackwell theorem. We can also achieve that using Cramarao lower bound. We're going to do that on Monday, and using the idea of exponential family of distribution. So this is where I'm going to stop today. Is there any question before I go today? Okay. Make sure you stay safe and enjoy your weekend. Bye for now, everyone. You're welcome.